thank you very much. So I'm going to start my presentation. So today I'm going to be doing a presentation on AI pathfinding, specifically in games. So, where the heck are we going? So this is an introduction for you. So the contents of this presentation. So the first thing we're going to do is we're going to have a look at a quick introduction and talk about Dijkstra's algorithm, one of the granddaddies in the area. Next, we're going to go on to the main topic of our presentation, which is looking at A star, which is a different kind of pathfinding algorithm. Next, we're going to have a look at heuristics. This is something that's very important to make our pathfinding work a little bit better. Then we're going to have a look at the real world implications of actually implementing pathfinding into a video game. And then a final section, which I like to call A star wearing glasses. I'm not going to explain what that section is now, but if you stick with me till the end, then hopefully that should be interesting for you at that point. Okay, so an introduction. So what is pathfinding, first of all? So you can imagine if you're you want to go to the Combini or something like that, you're going to use a lot of different senses. So you're going to use your eyes, you're going to use your memory of how you got there previously. But what if you're going somewhere that you haven't been before? So in that situation, you might rely on Google Maps, or you might rely on even a paper map or some directions someone's given to you. So you have all these senses coming into play. But if it's, for example, Google Maps, then that's going to take care of the pathfinding for you. But you're going to use your eyes for a little bit of fine tuning so you don't walk into any walls on the way there. So first of all, let's have a look at Dijkstra's algorithm. This is one of the oldest pathfinding algorithms. We're going to go through how this works. So please stick with it for now, and I'll explain. So let's pop a table on the left here. We want to get from A to E. So we're going to start out our table. A is going to be set to 0 because it's our starting point. The rest of them will set to infinity so that we can definitely find smaller numbers from there. Can't get much bigger than infinity. So let's have a look at A then. So from A, we can get to B. We can also get to C. We're going to look at all the places we can get to from there. So B, we'll set B in the table to 4 because we can now get to there for 4 from A. We're going to set C to 6 because we know we can get there from A for 6. So where are we going to go next? We're going to go to B because 4 is the lowest number. So let's move our way across to B. And where can we go from B? We can't go back to A, so the only place we can go is D. So we now realize we can get to D for a total of 9, 4 plus 5. So let's update our table. And then let's turn off B. We're done with B now, can't go anywhere else. So we've set D to 9. Where's our next lowest number? So our next lowest number is C for 6. So let's move our way over to C. And we can see there from C, where can we go? So we can go to D for a total of 8. So we're actually going to update D in the table. It was 9, but we now realize we can get there for 8. So let's update D. And we can now also, for the first time, get to E for 11. So we're going to update that in the table. And then where we're going to go next, we're going to go to D next. So let's make our way over to D. What new information can we get from there? So from D, we can go, we can't go back to B because, well, we can, but it's going to be a higher number. So we can go to E now for 10. So we found a route that goes from A to C to D to E, and that's going to be our final route to E. So Dijkstra's algorithm always gives us the shortest route. It always works. But let's see what problems we might have with it. So here is a real life implementation, so to say, of Dijkstra's algorithm and how it might work in a video game where you can move left, right, or up or down. Okay, so here's our starting point on the left. What's it going to do with Dijkstra's algorithm? It's going to look around itself at all the places it can touch. Okay, and from there, it's going to look around itself for all of the places those places can touch. And then we move through the algorithm, and essentially, this is what's going to happen. It's just going to keep checking the next nearest start point, and it's going to go round and round and round until it eventually stumbles across our goal. And then it finds the shortest path. So it does find the shortest path, but I think you can probably feel the inefficiency here. It's basically just it's searching behind itself, to the left, to the right. It doesn't feel very efficient. So how could we maybe improve that? Well, wouldn't it be good if it had some kind of senses? Maybe if it had a pair of eyes like humans do, or maybe if it had a sense of smell, maybe it could sort of more efficiently move towards the target. So let's now have a look at A star. This is the main part of our talk today. So this is the new and improved pathfinding algorithm, now with added eyeballs. So let's have a look at how it's different from Dijkstra's algorithm. It's still going to look around itself, but what it's going to do is we're going to give it a little bit of new information. And don't worry, I'll explain why this is the case later on. So we've got something called the G cost that you can see in the key, the F cost and the H cost. The G cost is going to be how far away from the start we are. The H cost is going to be the distance estimated to our goal, and the F cost is going to be a calculation of both of those two things together. So let's start off looking around ourselves. We have a G cost of 1 for all of them. The H cost, though, you can see is a little bit different. The H cost to the right and above start is actually 3, whereas it's 5. And that's because we're going, basically, we're calculating 1 point of movement for up or across. So from where it is to the east of start, it's going to be 1, 2, and 3 squares to get to the goal, and same for the one above. So for now, this is just to visually help. I'm going to grey out these two, which are a little bit more expensive in terms of F cost. So we're going to focus on these other two. Let's take the top one as an example, if we're going clockwise. And let's look around that one. So again, we can see the one closer to the goal is better than the other 2 6 ones. So let's grey those out for now. And now let's compare the two. And for the top one, the only real difference is that the H cost is smaller. And what A star does is it prioritizes, if there's a tie, it prioritizes the H cost. So we're going to choose the one with a H cost of 2. Okay, and then same situation here. We have two which are an F of 4, but the one at the top is clearly better with a H cost of 1. We're going to go here, look around ourselves again, and eventually we spot the goal. So we're done there. So as you can see with this, just by giving a little bit more information, it's stopped our algorithm from looking around everywhere and really focusing its attention a little bit. So let's do a bit of a demo to see this in action. So here we have a nice little low poly world that I've put together. And what we're going to do is we're going to have a quick look at an implementation of a pathfinding algorithm. So we have our start point on the left here, which we can move around, and you can see it's pathfinding towards our goal, which is over here on the right. So let's just move this behind a building, for example. So you can see here the yellow squares is the eventual path that it finds, and the red squares is the squares that it searched and it's actually checked and decided not to use in the end when it found the eventual goal. So you can see there that it's really quite a thick line from the start to the finish there because there's an obstacle. If there was no obstacle, for example, there wouldn't be any red squares anywhere because it's always able to move towards its goal. Okay, so that's a brief little introduction there to our pathfinding algorithm. Let's go back to the demo. Okay, heuristics, super important. And I've also titled this section, what kind of eyeballs can we attach? So heuristics is our ability to influence our pathfinding algorithm so that it can more quickly move towards its target. So let's have a look. So what is a heuristic? Putting the H in H cost. So it's a helping hand. It's another sense that we want to give to our pathfinding algorithm. And it also helps us adjust the decision we might want to make with our pathfinding algorithm between speed and accuracy. So that's two things we can modify with our heuristic. Okie dokie. So let's have a look at those. So just a quick warning here from the presenting team. The host of this talk takes no responsibility for the boringness of the next few slides. No legal liability is accepted for flagrant use of triangles, large words, or excessive numbers on screen at any one given time. So if you're still here, thank you very much. We're going to move into looking at the Euclidean distance. Here's a word that you can use at dinner parties to sound smart. So we've got our start point and our finish point. We want to make a h cost with our heuristic. So we could use the Euclidean distance for our heuristic. And what that does is it gives us an estimated distance to our goal. So how does it calculate that? So going across, it would cost 4 in movement. Going up, it would cost 3 in movement. But if we know how to make triangles, I don't particularly, so I'm going to skip over that for now. But if you have a look at the distance here, it's actually going to be 5. That's the actual length of that part of the triangle. By doing 4 squared, 3 squared is 5 squared. So that tells us then that the distance to the goal is 5, if we use the Euclidean distance. But the actual distance to the goal is 7. And that's because in our hypothetical game world, we can only move horizontally and vertically for 1 point of movement each. So please remember this word for later on, but that means that using the Euclidean distance in this situation would be an underestimating heuristic, which means that we're estimating the distance is 5, but the distance is actually 7 in real terms. Okay, the Manhattan distance. So the Manhattan distance basically allows us to calculate our distance to the goal by going across or up and down. So in this situation, it calculates our distance to the goal is 7 because it's 4 moves horizontally and 3 moves vertically. So the Manhattan distance here is perfectly assessing the distance to the goal. So that's great in this situation. However, let's have a look at the octile distance. Now, the octile distance also, instead of just moving up, down, left, right, we can also move diagonally. Now, as you may think, if you move diagonally, that's going to be a little bit more. If it only costs 1 movement to move diagonally, that's going to mean that we're going to just constantly zigzag around the map because there's no penalty for us doing that, even though technically we're walking a little bit further. So what we do with the octile distance is we assign a value to moving diagonally of, let's say, 1.4. And I think the actual real one is 1.414 or something like that, but we generally will choose 1.4 for moving diagonally. So if we look at the actual distance to goal here, it would be 7.2, and our octile distance is showing us 7.2. So that's 1, 2, 3 moves horizontally for 4.2, and 3 moves horizontally for 3. So that again is perfectly assessing the distance to the goal. But you can see if we use the Manhattan distance here, the Manhattan distance would tell us 1, 2, 3, 4, 5, 6, 7, 8, 9. It would tell us 9 to get to the goal, whereas it's actually only 7.2 in our game because we can move horizontally. So in this situation, the Manhattan distance wouldn't be perfect. It would be overestimating. So what is the result of over or underestimating? We're nearly through the super wordy section now, but not quite. So stick with it a little bit longer and we'll do some more cool 3D stuff. So an overestimating heuristic, which overestimates the distance to the goal, that kind of has the effect of biasing our pathfinding algorithm to move more away from the start and towards the goal. And we'll see why that is a little bit later. An underestimating one, it will tend to favor staying towards the start, which is going to result in this green area here, which is searched tiles, being much higher. We'll have a look at why this is the case. But suffice to say, an underestimating heuristic is always going to give us the shortest path. An overestimating one may not give us the shortest path, but it will get there super quick. So let's see why this is the case. So we're at the start. We're going to go through this section quite quickly, so please stick with it. An overestimating heuristic. So here what we're doing is it's 1, 2, 3, 4, 5 squares to the goal. We have a black wall in the way. And what we've done is we've just doubled the H cost for this one. So we've made the H cost much bigger, which is obviously overestimating. So it's not 5 to the goal. It's actually going to be, well, from this square here to the east of start, it's going to be 4 squares to the goal. We're going to call that 8. Let's see what effect that has. So let's grey out the two 12s and choose this square. Clearly, again, we're going to go forward there with an F cost of 8. Clearly, we're going to go to the 7. Now let's check the top one. It's a dead end. Now let's check the bottom one. Okay, and now we hit an F cost of 13. So we're going to start looking at the lower F cost. So we're going to have to go back here. So you can see the F cost is a little bit lower here. So we're going to get rid of that one. We're going to check here. We're going to go to the two 12s. And then finally, we can have a look at our 13. And because the H cost is lower, we'll choose this one. And then from there, it's fairly trivial. We'll keep moving towards the goal because the F cost is lower. Ta-da, we've reached our goal. Super. So let's now have a look. Oh, yeah, let me just say. So here's what overestimating is doing here. It's a bit like a bull in a china shop. So, you know, it's kind of smashing its way towards the goal. You ask the bull to leave your china shop if it can, and it's going to certainly make the decision on how to leave the china shop very quickly, but it might decide to, for example, leave through one of your walls instead of the door. So it has its benefits, but also its drawbacks. So let's have a look at the other case here. We'll have to get through this quite quick. So I'm just going to put everything on the screen at once. And one thing you can notice here is the H cost is halved. So that's lessening the value of our H. So what that's going to have the effect of doing is we're going to go to 3, 3.5 and 4. But here where we would have checked above and below before, these two, you can now see that the F cost is much lower towards our start. So we would check these ones, and we would check these ones. Now we'll have a look at these. Now we're going to have to go all the way back to the 5.5 over here. And we get to our goal. Still find the same path in this situation. But as you can see, with all the red squares that we've checked, using an underestimating algorithm makes our heuristic and our algorithm a very, very hungry girl. So there's a comparison of under and overestimating. Now, for people who don't trust me, let's have a quick look at a demo for this. So we're going to pop back across to here. Now, what we're going to have to do is we're going to have to modify our H costs. So we're going to pop into C# here. This is where our H cost is calculated. So let's divide it by 2. Save that. Now quickly update our script here. Hopefully it doesn't take too long mid-presentation. Okay, so you can remember before what the line was. Hopefully that Steam overlay goes away. Okay, click play. Wow. Okay, so you can remember what it looked like before, but now you can see that's a very, very hungry search algorithm now. It's finding the perfect path, but it's very hungry. So what happens if we overestimate it? Let's multiply it by 2. Save that, come back. Okie doke. Let's press play here. Okay, let's just move so we've got a building in the way. Let's move that here. Wow, now look at that. You can remember what it looked like before. Now there's hardly any missed or wasted search squares there. Again, I have to point out that this might not always give us the shortest path, but you can clearly see the benefits of overestimating our heuristic here. It's practically moving straight towards the goal with only a little bit of deviation. Great, good stuff. Okay, let's pop back to the presentation. So let's have a think about the real world. So what does this all mean? Is there a one-size-fits-all approach to pathfinding? Can we just always choose the same setup and boom, we're done? Definitely not. We can't do that. There's so many considerations to think about. One could be the map size. We might want a really accurate algorithm, but if it's a huge map size, as you've seen from underestimating, it's going to be very expensive in terms of how far it's searching around itself before it gets to the goal. We might have a limitation on hardware. People might be running this on a potato, and we need to make sure it's a little bit easier for them to run. We might have to think about the unit count in games. Do we have a one character to pathfind for? Do we have 100, 200, 300, 1,000 characters to pathfind for? We're going to have to obviously think about how accurate we want our algorithm to be in that case. We might have dynamic maps. We might have people getting in the way of things or destructible terrain. We might have to consider that and like how that affects our implementation. And we have to think about accuracy. Is it important that we have a perfectly accurate algorithm or not? Here's a great quote that I like. If you spend more time making sure it doesn't do something stupid, it will actually look pretty smart. And that's what we're going to go on to in our last section here, A-star wearing glasses. Now, basically, if you watch a movie, you might have just your average, dumb looking character, is an example in the movie. How do you make a character look smart in movies? That's right, you're going to put glasses on them. And instantly your movie character looks a lot smarter. So how can we make our algorithm look like it's a bit sentient? So one thing we can do is we can modify terrain and have that affect the algorithm. We could smooth some of those harsh lines out when the unit's actually moving. We could make groups of units react differently to each other when they're moving together. And we can also have collisions, for example, and how to deal with that. This is just some examples. We don't have time to go through all of these. So we'll have a quick look at a couple before we finish. So one is smoothing. We've got a start and our goal here. Maybe this is the route our pathfinding algorithm takes. But what we can do is we can have points in here and take these red points, and then let's actually have our algorithm turn on the way to the second point and then turn again on the way to its next destination. This fluidity might make it look a lot more intelligent when it's pathfinding. Now, terrain. Now, we could have a few different types of terrain. Impassable. But what we can also do is we can make it harder to pass some parts than others. Or we could make it easier to pass for some parts than others. So you can move super fast through that territory. So now we're going to have a see if we can see that on our demo again. Okie dokie. So let's take a look at our A-star. Now what I'm going to do is I'm going to put in a terrain penalty for the grass of 5. And I'm going to put a terrain penalty for the little pond over here to 10. And I'm going to save that. So let's just check. We've reset in C#. We need to remove our overestimating algorithm. Okay, so let's see what effect this has. So let's press play here. Okay, so interesting. So now you can see, if we just, let's try and full screen this. Okay, so now you can see here that what the algorithm is doing is it's moving onto the road and it's favoring the road when it's making its movement decisions. And that's because basically it's just quicker for it to get there. Let's go behind this pond, and you can see how strongly it's trying to avoid the pond there because of the huge movement penalty it would take. And in this way, we can really make it look like our pathfinding algorithm is quite intelligent. So let's pop back to our demo. And that's basically the end of our presentation. So we'll just do a quick conclusion. You can modify the terrain and some other aspects of the algorithm to really make it look like it's intelligent. You can also mess with the heuristic, so you can make it move towards the goal a lot more quickly at the cost of some accuracy. So we need to consider all of these things together to make our pathfinding algorithm look quite good and quite smart. I hope I've been able to do that at least in part today. I'd love to talk about it more. There's so many topics in here to discuss. It's a really rich area to go through. So I'd love to talk to some of you about it later on. Thank you very much for listening to the presentation today. A couple of tips for further reading. Flow fields is super interesting, and that's an implementation that helps you with lots and lots of units in a game. And thank you very much for Sebastian Lag's tutorials online. They were really instrumental in helping me understand how all of this worked and getting this presentation together today. And some other research articles and things that were super good as well. I'll move on to my final slide. Thank you for listening. Please grab me on Twitter or LinkedIn or GitHub there. And thank you once again so much for listening. I look forward to burning your ears off with this topic some more later on. Thank you very much. Back to you, Jan.